In this video, we're going to cover section 6.2, assignment of probabilities. So a probability is a numerical measure of the likelihood that a specific event will occur. Numerical measure, that just means a number. Numbers between 0 and 1 is called the probability of the event. If an event has a probability of 0, it's impossible. 1 is certain. Okay? The larger the number, the more confident we are that the event will occur. There are three types of probabilities. So a logical probability is obtained by mathematical reasoning. So we've got counting techniques of the previous chapter. So we could calculate the probability of a coin toss showing heads, obtaining a full house in poker, or winning a Powerball lottery. Empirical probability is obtained by sampling or observation. It's calculated by dividing the number of times the event occurs by the total number of observation. This value is also called the relative frequency. So some examples are as follows. The probability a certain brand of light bulb will last more than 1,000 hours. Probability a person selected at random will be a smoker. Probability that taking small amounts of aspirin daily will lower your risk of having a stroke. So these are observations, things that we don't know the exact way to calculate, or it is incalculable, and so we just do experiments or observation. And a judgmental probability is an educated guess, also a subjective probability. So some of these, New England Patriots will win next year's Super Bowl. Probability a Democrat will be elected in 2020, I guess this is dated a little bit, 2028. Probability you'll get an A on your next math exam. So these are things that we could reason out and have a judgment about, but not necessarily a mathematical calculation. So classifying the following probability as logical, empirical, or judgmental. Probability it will rain tomorrow. This is empirical. We can take the calculation just in general, take that calculation or what is going on, what has happened today, in the forecast, and determine that probability. So sometimes we have an event that has a lot of different outcomes, and so we can list out these outcomes, outcome 1, outcome 2, all the way down to the last outcome, and assign their probabilities. This is called a probability distribution for an experiment or an event. And there are two probabilities that each of these numbers is between 0 and 1, and if you add all the probabilities up, it has to equal 1. Okay? So, example 2, determine the probability distribution for the following experiments. Toss an unbiased coin and observe the side that faces upwards. Well, we have heads, we have tails. So the probability of heads is 1/2, the probability of tails is 1/2. So, notice that total equals 1. Now let's roll a die and observe the side that faces upward. So that would be 1, 2, 3, 4, 5, 6. Those are different possible outcomes. And each of these will be 1/6, giving us a total of 1 as well. A group of 141,000 college freshmen were asked a question, what is your intended major? Table 1 shows the result of this question. Consider the experiment of selecting a student at random from the group and observe their answer. So determine the probability distribution for this experiment and verify the probabilities satisfy the properties 1 and 2 in the chart above. So what we have to do, what is the probability that somebody is in arts and humanities? So the way that we do this is we take that 14,241 and divide it by the total, 141,000, and that'll give us an answer of 0.101. So the probability that a student is selected who is and arts and humanities major is 0.101, about 10%. We'll do the same thing. 21,000 divided by 141,000 is 0.149. And we'll do this with all of these. 0.134, 0.131, 0.113, 0.081. Social science, that's 0.108. And other and undecided is 0.183. So to verify these, let's just take a glance up. The first property says that all of these are between 0 and 1, and they are. Most of them are in the between 10 and 20%, but they are all between 0 and 1. And now we need to add these up and verify that these do equal 1. And so we can add these up and verify that that is 1. Now, sometimes when we round these, we might get like 0.999 or 1.001 just because of how we rounded. That is okay. If we've rounded those values, we can understand that this has a value of 1 just because of a rounding error. We didn't get exactly 1. The addition and inclusion-exclusion principles. So suppose that we are given an experiment with a finite number of outcomes. So now we assign each event a probability that we denote by the probability of E. So that's the notation. So this is probability of an event. If it consists of a single outcome, it's called an elementary event. If it consists of more than one outcome, we may compute the probability of that event by the addition principle. So the addition principle, suppose that E consists of a finite number of outcomes, then the probability of E is STU, add all these individual probabilities. Okay? The probability of an impossible event is 0. So let's look at, this seems a little confusing, but let's just talk about an example and it will make more sense. Suppose we roll a die and observe the side that faces up. What's the probability that an odd number will occur? So what's the probability of odd? Now this is not an elementary event because it's made up of different options, 1, 3, 5. So to find the probability of this, we're going to use the addition principle. What's the probability of 1 plus the probability of 3 plus the probability of 5? And we know that's 1/6 plus 1/6 plus 1/6 is 3/6 or 1/2. So that's all that addition probability means. Probability distribution for the number of boys in 2-child families. Observe the genders and birth orders in 2-child families and calculate the probabilities of 0, 1, and 2 boys. So what we're going to do is we're going to make a chart here just to look at the options. So we have one kid, could be female or male, and kid 2, we'll call it kid 1, kid 2, could be female and male. So we could have both females, then male, female, female, male, and male, male. So probability of 0 boys is 1 out of 4 chance. That's where you get the female, female. Probability of 1 boy is 1/2 chance, and probability of 2 boys is 1/4 chance. So again, we add these all up, and that equals 1, and they're all between 0 and 1. So that's the probability distribution. Let's look at example 6, probability associated with college majors. So we're going back to example 3. What is the probability that a student selected at random from the group surveyed intends to major in one of the 3 most popular fields outside of the other and undecided choice? So the 3 most popular fields, would be biological science, business, and engineering. So probability 3 popular is found by looking at biological sciences, business, and engineering. So we're going to take the probability of biological sciences plus the probability of business plus the probability of engineering. And those probabilities are 0.149 plus 0.134 plus 0.131 equals 0.414. So just over 40% of the students have chosen the 3 most popular fields. Probability associated with the roll of a pair of dice. Suppose that we roll a red die and a green die and observe the numbers of sides that face upwards. Calculate the probabilities of the elementary events. We discussed this in a previous section where we had 1, 1. So let's say this is the red and this is the green. And then we could have 1, 6. All the way down to 6, 1, where this is the red and this is the green. And 6, 6. Now, because of the colors, we don't swap. Every single one of these is independent. It's different. And because they're all equal, everyone has a 1/36 chance of occurring. Now, calculate the probability that 2 dice show the same number. That's going to happen along the diagonal. 1, 1, 2, 2, 3, 3, 4, 4, 5, 5. So there's 6 out of 36 ways that occurs. So the probability will be 1/6. A person playing a certain scratch-off ticket can win $100, $10, or $1, can break even, or can lose $10. These 5 outcomes with their corresponding probabilities are given by the probability distribution in Table 3. So here's Table 3. So there's a 2% chance of winning $100, 5% chance of winning $10, 40% chance of winning a dollar, 3% chance of breaking even, and 50% chance, this is 0.03, and a 50% chance of losing. Which outcome has the greatest probability? That would be losing $10. And usually how this is designed is that's the $10 you spent on buying the ticket. Which outcome has the least probability? $100. What is the probability that a person will win some money? Well, that would be 40%, the 0.4, plus 0.05, plus 0.02. So that would be 0.47 is the probability of 47%. The inclusion-exclusion principle, this is very similar to what we've covered before with sets. The probability of the union is the probability of the two individual probabilities minus the intersection. So again, when we did this with sets, we had the 2 sets. Here's E, here's F. If we add E plus F, we've added this middle part twice, and so we have to subtract it. If they're mutually exclusive, meaning they can't happen at the same time, then we don't have to subtract the intersection because the intersection will be 0. All right, example 9. A factory needs 2 raw materials in order to operate. Probability of not having an adequate supply of material A is 0.05, whereas the probability of not having an adequate supply of material B is 0.03. A study determines the probability of a shortage of both A and B is 0.01. What proportion of the time can the factory operate? So we can use our inclusion-exclusion principle to show that the probability of running out of A and B would be the probability of running out of A plus the probability of running out of B minus the probability of running out of both of them at the same time. We know these values, so this is 0.05 plus 0.03 minus 0.01. So the probability of the time we have run out of A or B would be 0.07. So the question is, what proportion of the time can the factory operate? Well, we take 100 minus the 7%, so 93% or 0.93% of the time, they would be able to function because they have both a supply of both materials. All right, converting between odds and probabilities. These are very related things, but they are calculated slightly different, and we need to make sure we understand that difference. So if the odds in favor of the event E occurring are A to B, then the probability of E equals A over A plus B. Now, as we do some examples, you'll make sense of that, and maybe you can make sense of it already. So that's how you go from odds to probability. Now to go backwards, if you have a probability as P, then the odds are found by reducing this fraction, P over 1 minus P. So let's do this example 10. So suppose the odds of rain tomorrow are 5 to 3. So what is the probability that rain will occur tomorrow? So that means there's we could say 5 chances that it will rain, and 3 chances will have no rain. And so 5 chances of rain over how many chances total is 8. So 0.625. Notice we took that A over A plus B, added the chances or opportunities together, and we got 0.625. The probability of obtaining a sum 8 or more when rolling a pair of dice is 15 to 36. What are the odds of obtaining a sum of 8 or more? So we're going to go from probability to odds. So 15 are the chances of 8 or more, so greater than 8 or equal to. And so how many? 36 is the total, so we subtract 15 to get 21 is less than 8. So it's 15 to 21 that we will get a sum greater than 8. And that would divide those by 3. That's 5 to 7 chance. The odds of obtaining an 8 or more are 5 to 7. Now, example 12 is a paradox. Paradoxes, counterintuitive results abound in probability. So on December 1st, 1996, issue of Parade magazine, Marilyn Vos-Savant presented the following question in her column, Ask Marilyn. A woman and a man who are unrelated each has 2 children. At least one of the woman's children is a boy, and the man's older child is a boy. Does the chance that the woman has 2 boys equal the chance that the man has 2 boys? So we have a woman, we have a man. They're not married, they're not related. They each have 2 children. So kid 1, kid 2. At least one of the woman's children is a boy. So boy or boy. And the man's older child is a boy. Does the chance the woman has 2 boys equal the chance that the man has 2 boys? So let's calculate the man first, because it's much easier to determine. We already know the oldest is a boy, and so the probability that the second one is a boy is 1/2. So the probability that the man has 2 boys is 1/2. Now, if we look at the woman, there are 2 options. The first could be a boy, and then the second one could be a boy. The first one could be a boy, and the second one could be a girl. And the last one is the first could be a girl, and the second one could be a boy. So there are 3 options here, and they're all related. So the probability that the woman has 2 boys is actually 1 out of the 3, 1/3. And so, does the chance that the woman has 2 boys equal the chance the man has 2 boys? No, it does not. Because of the way they've stated it, it is a lower probability that she has 2 boys. And that finishes our notes for section 2. Thank you for watching.